Hello, good evening, good day. It's our April series of lectures on doing earthquakes, modeling and simulation, realistic modeling and simulation of earthquakes, soils, structures, and their interaction. Today we're gonna spend some time talking about seismic motions. Together with me are Dr. Yang. Hi,
Hello.
And Mr. Wang, Hessian, hello.
Hi.
They're both in Davis. I'm in Zurich, in Switzerland. It's the first day that they slowly start to remove the restrictions in Switzerland, this coronavirus quarantine. In Davis, not yet, I guess, a week or two away, but in California, we'll see how it goes. Anyway, so we'll start. Let me share my screen with you. And I hope you can see this is the front page. We're gonna split this lecture into two lectures. First part, we're gonna talk about introduction, and then a little bit about ground motions. And then the second part, we're gonna talk about a little bit more modeling of ground motions. So one of the big questions I always ask people is, how many earthquakes have you lived through? Have you felt earthquakes? And you two guys, have you felt, Han, have you felt earthquakes in China or here in California?
Yeah, I think I did one time, a small one back in China, and a few also small ones here in California. Yeah.
Did you so in China, the one? I mean, were you in a building or outside or?
I think I was actually in the movie theater.
Oh.
So I was not sure whether it was the movie effect or the earthquake, but later I found out it was an earthquake.
Okay, but nobody left. No panic, nothing.
No, it was just one small shift that I felt.
Okay, yeah, I felt the same thing. And then Heshan, you felt some big or small earthquakes?
Yeah, I remember that big one, like 2008, like the Wenchuan earthquake.
Oh.
I felt that one. Yeah, when I was like junior high school. Yeah.
So how far were you from the epicenter?
I know it's pretty far. I think probably half of the whole China, halfway of the whole China.
Oh, so that's almost 1,000 kilometers or a little bit less maybe.
Yeah, but it's very tiny shaking. Yeah.
But remember that the earthquake was felt in Tokyo. They said that the big buildings in Tokyo were swaying. This is 1,500 kilometers away. That was a big earthquake.
Oh. Yeah.
And what you felt was mostly surface wave. Right? Anyway, we'll talk about it. I did feel quite a few earthquakes when I was a kid. I remember 3 or 4 big ones. One woke me up on Sunday morning. One took some figurines from the TV and from some shelves. One I was actually taking a shower, and I always was proud to say that any of these other earthquakes, I would always run around, turn off the electricity, turn off the gas. For this one, when I was in shower, I swear I opened my eyes and I saw the tiles on the wall go like this, which is impossible, but I was scared. I ran out with just a towel, just ran out of the apartment completely. And then in California, I think I felt 2 or 3 earthquakes, one in movie theater, one in the building in my office, and then I think one I was in the house. Anyway, so most of these earthquakes, what we feel usually is horizontal motions because we are in the buildings, and most of the time buildings are very soft this way, and rarely you feel actually verticals, although both of those are present. So the motivation of our work is really to improve design, seismic design and design in general of infrastructure objects. And to be able to do that, we would love to use high fidelity numerical models to analyze seismic behavior of soil foundation structure systems during earthquakes. We would like to be able to follow seismic energy as it propagates through soil and the interface zone and foundations and the structure. And by changing shapes and changing materials, maybe direct in space and time the flow of seismic energy so that we make those systems safe and economical, of course. There's an interesting story that I read some time ago in a book. Certain professor, Kyoji Suyehiro in Japan, was a professor of naval engineering, professor of shipbuilding. I mean, mechanical engineering, but actually shipbuilding. Happened to be in downtown Tokyo during a famous Kanto earthquake in 1923. And that was a big earthquake that actually had 3 main shocks, and it lasted for almost 10 minutes or a little more. And he was apparently downtown, and it started to shake, and he, it's a primal fear, it's a panic. And he stood there apparently, and he held the building to not fall down. It was a very strong earthquake, and Tokyo is a very soft ball of essentially clay and mud. And so the whole Tokyo was shaking a lot. And then he saw buildings sway. If you look along the street, you see buildings, how they move. Even if you look on YouTube, you can find some pictures of some buildings swaying during earthquakes, current modern buildings. But at that time, this was almost 100 years ago, 97 years ago. He saw buildings sway, and he thought that the mechanics of that swaying is very similar to ships. When the ships are on the ocean with waves, they do this. They also go back and forth. So he quit his job as a professor of naval engineering and became a founding director of the Earthquake Engineering Research Institute at the University of Tokyo. And then actually started doing research and published a number of papers on that, and then came to US in 30s to talk about his work and what the earthquakes do, and published 3-4 papers. I think we have them. I have them from 1932. And then unfortunately got sick on the way back, and it was a ship travel. It took a few weeks at least, and then passed away when he got back home. Very sad story, but he was the founding director of ERI in Tokyo, professor of naval engineering, naval architecture at the University of Tokyo, who switched over to become earthquake engineer. This is one hypothesis I heard from Gazetas a long time ago. The interplay of interaction of earthquake and soil rock and the structure in time domain plays a very important role, a major role in all the possible failures and successes. Most of the time we actually do have successes. Not all buildings fail. Some buildings fail, some bridges fail, some objects get damaged, but a lot of times we actually do have successes. The main point is that timing and location of energy dissipation determines location and the amount of damage. And if we can control by making different shapes, by making different types of structures using different materials, if we can control this timing and location of energy dissipation, we can direct it, we can design better soil structure systems. We could optimize the soil structure system for safety and economy, and that's really important. In this first 10-15 minutes, we're going to talk about seismic motions, ground motions. Important to note that there are body waves, the waves that propagate inside the half space, inside the body down. There are P waves, so-called primary waves, and S waves. P waves are called P waves, primary waves, because they come first. Those are compressional waves. When there's a slip, there will be one component that's going to be essentially compressional wave. They travel very fast, and they're the first one to show up at the surface, and they're the first one to be recorded. Those are P waves. After them come S waves, secondary waves. They're essentially waves that travel like this. These are shear waves, and they travel slower, and they show up later on. There are so-called Stoney waves. Those are waves between different layers. Usually we have layers underground. Then when these waves surface, they produce so-called surface waves, Rayleigh waves, usually regular waves. I'll show examples. And then lob waves, which are kind of twisting waves that go like this. There are a number of important effects with all these waves. They're so-called lack of correlation, incoherence effects. Waves are going to travel through different domains, and they're going to end up with different at the surface in very close proximity. Let's say within 100 or 200 meters, they're going to look different, sometimes more different, sometimes less different. They're always inclined waves. Usually we analyze them as vertically propagating shear waves and P waves. They're rarely vertical waves. They're usually inclined waves, and that can make a difference. There are 6-component waves, 6-dimensional waves, 6-component waves. What I mean by that, there are always 3 components. There are 2 horizontal components, and there's a vertical component, and at the point, and there are 3 rotations. So 3 translations and 3 rotations. Rotations are on this axis, and this axis. And so this is really important to understand. Now, when I mentioned the vertical components, if I have 2 points and I have 2 vertical components, and they do this, that's a rocking motion, that's a rotational component. And this distribution of waves makes a difference, can make a big difference in how this energy is distributed and how is it dissipated. The main question is, how are these realistic waves affecting our soil structure systems? Here's an example. Let me start this animation. This is a very simplistic example. We'll use this example later on to show some more effects of these surface waves. Here's a point source, which is very unrealistic, but just to show what happens. One point where there was a slip, there was an element like this that kind of slipped and started oscillating. There are layers down at 400 meters and below. There's a very stiff layer. Then here between 150 and 400 is a softer layer, and there's a relatively soft layer on the surface. And please note how these waves propagate. They're going to reflect and refract when they hit the boundary. The waves that are at this interface are called Stoney waves. This boundary is going to create a new set of P waves and S waves. And you'll see P waves, they're first waves to travel because they're faster. They're going to hit the surface and they're going to create S waves. They're going to create Rayleigh waves on the side. So let's continue with this. I'll show you zoom in of this section in a second. So see, these are P waves, and then they start floating up here, and then they start floating sideways as Rayleigh waves. You see how different reflections and refractions are at the boundaries. This deep layer is a stiffer layer, so these waves are going to travel faster. This is the same wavefront as this wavefront, and then they travel up to surface. So now what I'm going to do, I'm going to zoom in on this section here. I'm going to zoom in on this section and show you what happens when these waves reach surface. Let's stop this. Let's go to next slide. Here's that same location. Again, this is not a structure, just a location, just to show that this is the same location. Let's look at this. Again, that interface is right here. And you can see when these waves, these are P waves, they go straight up and down. But when they go sideways, they become Rayleigh waves, and they start to actually produce surface waves. In this case, only Rayleigh waves, because we're essentially in this one plane. And so you can see how these waves travel, and now there are positive and negative interferences. Mr. Wang is going to talk about that in a few lectures, and how we calculate those and how they become, and how do we analytically analyze systems like this. So they travel out of the system. Usually we do have horizontal layers. However, sometimes we do have actually inclined layers. If you have horizontal layers, it's usually that the soil or rock is getting softer and softer as you get close to surface. And because of Snell's law that says that when the wave propagates from faster medium to slower medium, it starts to bend. In this case, waves are going to start to bend toward vertical. Waves that come close to surface are close to vertical, but not vertical. Depends again about the layering effects. Depends on what's the geometry of layers, and it also depends on how deep and how far away is the actual fault. So they will get close to surface in almost vertical, ideally, but never really vertical. So maybe 10, 15, 20 degrees of vertical, maybe sometimes even more. If you have layers that are quite a bit different, you can actually have a very complicated picture of these waves. And it's important to be able to understand, to know what's the geology beneath, and to be able to understand what the effects these waves will have on your object. In this case, some type of power plant. So geologic layering makes a big difference. There will be this positive and negative interference, how far from the fault you are, and there will be also interaction with the structure, and that's going to contribute to occurrence of these multidimensional waves. Here's an example of this earthquake from 9 years ago in Japan, the Great Sendai earthquake. You see how Japan has a lot of measuring stations. This is that line of measuring stations, one of the lines of measuring stations. And you can see how the waves came. Apparently, one of the hypocenters was down here deep, and then there was one slip, and you see how the wave fronts goes by. By the way, please note, this is going from 0 to 50, 100, 150, 200, 250, 300 seconds. So that's 5 minutes of shaking. So there was a first slip, there was a second slip, and apparently there was a third slip that started a little further away. Apparently the slip area was 600 kilometers by 200 kilometers. So 600 kilometers from about here to Tokyo is about here to about here, and then 200 kilometers from about here all the way under Japan. So very complicated and earthquake, large, huge earthquake. What I showed was our accelerations. What I'm showing here are displacements, significant displacements. And interestingly enough, Japan is now closer by about 1 meter, 1.2 meters to US, and it's this coast here is now lower. There was a permanent slip down, so this coast is lower by about 80 to 90 centimeters, about 3 feet or so. These are motions that are measured in Tokyo. Let me show you where that is. So the epicenter was here and here in the ocean, and then here, and Tokyo is here. But see, Tokyo is a big flat geology. There's no topography really. It's all very, very soft soil. So these are the actual motions that were measured. Oops, going the wrong way. These are the actual motions that were measured in Tokyo. Significant displacements. Look here. Almost 30 displacements down, 20, so almost half a meter going up and down in Tokyo in a few seconds. Here's an interesting animation that's actually on Japan Quake Map. I'll start this website. This is a website, so let me just stop here. So what this does is I'll stop. I'll make these sticky points. This is the Pacific plate that's actually going under Asian plate, and there's actually a zone here that's a crack, and this crack was the source of that great counter earthquake in 23. And in all the reports before this big earthquake, everybody was expecting a big earthquake to come from this region here. They knew this is going to have an earthquake, but not that soon. So it turns out that this plate, there was a subduction zone that went under. It slipped here and went all the way down. And so the slip was happening between approximately this line here and this line here. The interesting and scary part is that now, because this zone here slipped a lot, it slipped a few meters or more, there's even more strain at this crack here. So this earthquake is even closer. So what this is doing, this is going to show locations of epicenters, and the size of the circle is going to actually be, let me show you one. Let's wait for one. I should speed this up. So the size of the circle is going to be the size of the earthquake, and they're going to be listed on the side here. But you also see the depth here. These are fairly, this goes down about 40, 50 kilometers, but some of them are going to be shallower. So you'll see how this whole section is going to start popping like popcorn as the slip happens, and as this Pacific plate, the one that is here, starts to go under Japanese plate. And because of that, Japanese plate first pushes up and then pushes down and then moves closer to the US. So let's follow this sequence here. I'm going to speed up a little more. And here's the big one. That previous one was a big one. Please note how they actually experienced. Remember, the first one happened, the big one happened on March 11th, 1446, so about 2:45 in the afternoon. And then let's look a day later. So 1443 on 12th. Still more to go. They had a lot of small earthquakes in between. Here is about 1458, that about here. A lot of earthquakes, a lot of slippage, a lot of shaking in Japan in that one day and a few days later. And you see that, 200, 300, 400 earthquakes. And those are not big, small earthquakes. They are, 5s and 4s and whatnot, and you can feel some of those. Actually, most of those 5s you can feel. So there was a lot of shaking in Japan. A lot of shaking in Japan anyway, but this was a lot of shaking from that earthquake. So again, this is at japanquakemap.com. They actually have links to some other ones and to energy release and whatnot. Very interesting website. So going back to our presentation, all these motions are full 3D. 6 components, 3 translations, 3 rotations. There are very few motions that have only 2 components. I've never seen a 1 component earthquake. I've been looking for a really long time. Here's a famous case, the so-called LSST-07 in Lotung in northeast Taiwan. This is the one that had 2 horizontal components. This is the north-south component. This is the east-west component. Up and down component was very, very small. It's almost like there was just shaking like this, nothing vertical. This is one of the really rare earthquakes. This is LSST-07. This is special arrangement of geology, source, and path that produced this earthquake. Exactly same location. A few months later, produced an earthquake like this, the so-called LSST-12. And this one had all the components, both P waves and S waves and surface waves and so on. So this is a very rare event, but it's usually used actually for validation because it actually does feature only shear behavior. There's another earthquake that was recorded a few years back that almost won the earthquake. This is from Strong Motion Center website. This earthquake had a very much direct effects in this direction, and these are displacements and accelerations. Very much a lot of directivity in this earthquake. But these are very rare earthquakes. In general, there are three component earthquakes, and we'll spend time on that. So with this, I'll stop, and then we'll continue in our next lecture. So I'll stop sharing, and I will stop recording.